For this explanation, I'll talk about the visible light spectrum and three specific light waves: red light, yellow light, and blue light. As you can see, each type of visible light has a different wavelength. The wavelength corresponds to the frequency. The longer the wavelength, the lower the frequency. The shorter the wavelength, the higher the frequency. Higher frequency results in a higher energy light. The classical wave theory of light thought that the more intense the light was, the higher energy that was. Light intensity in the classical sense can just be thought of the amplitude of that light being larger, or there's simply just more of that light. The photoelectric effect can be observed by when you shine light on a piece of metal, the metal will release electrons in some situations. As you can see, the blue light causes an electron to be emitted by the metal, but the lower frequency red light does not cause an electron to be released. This is a result of something called the work function. The work function is the amount of energy required for an electron to be emitted from a certain type of metal. Every type of metal has a different work function. So, according to this reasoning, the reason why the red light didn't emit an electron because it didn't have enough energy to overcome the work function. But the higher frequency blue light did have enough energy, so that's why the electron was released. So according to the classical wave theory of light, if you simply shine a more intense light on the metal, an electron should be released. When they conducted this experiment, that even with a more intense light hitting the metal surface, that when it made contact, an electron still wasn't released. The result of this experiment was very confusing for classical physicists and could not be explained using the classical wave theory of light. In order to explain the results of the photoelectric effect, a new way of thinking was required. This is where Einstein proposed his idea of light as a particle. Einstein proposed that light behaved both as a wave and as a particle, and that it had wave-particle duality. He proposed that light was composed of individual particles, each with their own energy, called photons. Einstein continued the work that had been begun by Max Planck. Planck proposed that all matter was composed of specific quantities of energy, called quanta. Einstein carried this over into light, but instead of quanta, he called it a photon. The energy of the photon is equal to h times frequency. H represents Planck's constant and is equal to 6.3 times 10 to the negative 34 meters squared kilograms per second. The energy of a photon can also be expressed in terms of wavelength. When we look again at the different wavelengths of light in our examples, we can see that blue light has the smallest wavelength and thus will have the largest energy because it's being divided by a small number. And red, having the longest wavelength, will have the lowest amount of energy because it's being divided by a large number. The realization that light was composed of photons and that the energy of the photon was dependent on the frequency or wavelength helped to explain the photoelectric effect and how that when you increased intensity did not lead to an electron being emitted by the metal. And that even if you shone an extremely low intensity of blue light on the metal, an electron would still be released. Each metal has a certain frequency that's needed to be reached for an electron to be emitted. This frequency is called the threshold frequency. According to Einstein's particle theory of light, no matter how intense the light, if the frequency did not meet the threshold frequency, no electron would be emitted by the metal. In our example, our metal has a work function equal to 2.2 electron volts, or 3.5 times 10 to the negative 19 joules. We can find the threshold frequency by equating the work function to the energy of the photon. A photon that has the threshold frequency has just enough energy for an electron to be released. We see now that work is equal to Planck's constant times the frequency. We can rearrange this formula to solve for the frequency. We can see now that we need to divide the work function by Planck's constant. which is equal to 5.28 times 10 to the 14 hertz. We can now use the threshold frequency to find the wavelength that this corresponds to. Wavelength equals the speed of light divided by the frequency, which is equal to 5.7 times 10 to the negative 7 meters. This can also be written as 570 nanometers, which, as you remember, is equal to the wavelength of our yellow light. As we've just established, the yellow light represents our threshold frequency. So when yellow light hits the surface of the metal, the electron is released, but it has no kinetic energy. If we remember with the blue light, the electron was released with a certain velocity and traveled away from the metal surface. In this situation, that does not occur. This leads to the next realization of the photoelectric effect. If the frequency of the light shining on the metal is greater than the threshold frequency, the leftover energy, so to speak, will be converted into the kinetic energy of the electron. The energy between the photon and the electron is conserved. The kinetic energy of the electron can be found by taking the energy of the photon minus the work function. As we just demonstrated with the yellow light, the energy of the photon of the yellow light is equal to the work function of the metal. So the kinetic energy of the electron is equal to 0. But now if we consider the blue light from the example before, how do we find how much kinetic energy that electron had? Using the wavelength formula for the energy of the photon, we get this equation to find the kinetic energy of the electron for blue light. Once we plug in Planck's constant, speed of light, divided by our wavelength of blue light, minus the work function for this metal, we get the answer 7.3 times 10 to the negative 20 joules of kinetic energy for the electron released when we shine blue light on the metal. We now know the kinetic energy of the electron is 7.3 times 10 to the negative 20 joules, and we know that the mass of an electron is 9.11 times 10 to the negative 31 kilograms. So we can use this information to find the kinetic energy of the electron. Just like a collision between two cars, the collision between the photon and the electron, energy is conserved. We know kinetic energy to be equal to 1/2 of mv squared. We can rearrange this and solve for v. Once we rearrange this, we can find that the velocity is equal to the square root of 2 times the kinetic energy divided by the mass. Once we plug in all the values, we can find that the speed of the electron emitted when blue light is shone on the metal is equal to 4.0 times 10 to the 5 meters per second. A great simulation to look at the effects of the photoelectric effect. As you can see by the screenshots, you're able to adjust the wavelength, the brightness, which can also be the intensity of the light, the voltage between the two plates. Potassium is the metal that the photons are hitting. You also have a screen on the other end that detects the number of electrons that are reaching the screen. I've placed my voltage at 0 so they can flow freely through the difference between the two plates. As you can see from the screenshots, a blue light, which is wavelength of 470 nanometers, just like in our example, it will emit electrons from the potassium. As you can see, if the brightness or intensity is at a minimum, electrons will still be released. In this situation, only 1 electron is released. As we increase the intensity, more electrons are released. Each photon can cause the release of 1 electron. The intensity will just increase the number of electrons that are emitted. See, as we begin to increase the wavelength and decrease the frequency to green light, electrons are still emitted, but as you can see when you do the simulation, that their speed is less. This means that the photon hitting the metal has less energy, so the kinetic energy of the released electron is therefore less than it was with the blue light. When we increase the wavelength further to our red light, we can see that no electrons are emitted from the metal, no matter how intense we make the light. This is because the frequency of the red light is below the threshold frequency. So no matter how intense the light, no electrons will be emitted. This is a great lab to show the visual representation of this effect as well as allow you to play around with the different wavelengths and brightness to see the effect firsthand.